this section discuss the method to solve two-dimensional wave equations. We discussed one-dimensional wave equation a couple of times with different kind of method. Actually, we used at least 3 kinds of methods, right? to solve the one-dimensional wave equations. One example is by using the method of separating variable, using the method the numbers method, or we can use Laplace transform. Okay, so this time we would like to use to consider two-dimensional wave equations, this wave equation is to model rectangular membranes. So this is the case that so in general, so we have a membrane. Okay, so we have a membrane which is rectangular, and then we want to apply some initial displacement on the membrane so that it will vibrate vertically. Okay, so the vibration is out of the breakboard and into the breakboard, something like that. So the vibration is vertical. Yeah. Okay. And so you can think about, you have a rectangular drum there, okay? And so probably we may hit the drum, okay, at initial time, so that you will produce some disturbance on the membrane, okay, as the initial displacement of the membrane, and also initial velocity of the membrane, okay? And then you will observe the vibration of the membrane as time evolved from 0 to 0. Okay, so this is the physical phenomenon for rectangular membrane. So we let u, x, y, t be the vertical displacement, okay, of a point x, y of a vibrating rectangular membrane. Okay. And this membrane locate on the region. So the region I will call it R. Okay. So the x extended from 0 to A, y extended from 0 to B. So this rectangular membrane is in the xy plane. When at rest. Okay. 20. So if we do not disturb the membrane, then the membrane will be at rest on the plane. However, we do not apply any force or any disturbance on the membrane. All right. Now, the displacement u x y t, right, will be governed by a two-dimensional wave equation. The rectangle, or so we have equal to right, and this is true for right. So this two-dimensional wave equation is valid for all points in the rectangle and for t greater than or equal to 0. And we will put the boundary conditions. So the boundary condition on the boundary will be denoted by dr of the rectangle. Oh, okay. So we will, and we will put a simple boundary condition that the displacement, okay, of the displacement at every point on the boundary will be 0 for all time. So okay, so this is the boundary condition. So basically you can think about that the membrane is fastened all right, along the boundary. Okay. So this is the situation. That's good. All right, so we have boundary conditions here. Okay, and two initial conditions that we have the initial displacement okay, and the velocity of the displacement is described by g function. Function here. And because of the boundary condition, know that from the boundary condition, we have that xy equal to 0 for all xy in the boundary of the rectangle, and the g of xy is 0 for all xy on the boundary of the rectangle. Okay, so we know that. So this is a consequence from the boundary condition and the initial conditions. Any questions? So this is our problem. We need to solve this problem. Okay. All right. So let me put the name here. It's 2.1, 2.9.2, okay, 2.9.3, 2.9.4. So we will solve the problem. From 12.9.1 to 12.9.4, okay, by the method of separating variables. Successively, maybe I will say right. Because of time limitations, I can just give you the idea, right? So first, relate u of x, y, t equal to f of x, y, and the gt. Right. So first of all, we separate. We assume the solution is a product of a function of x and y and a function of t only. Okay? So now, so implies that we have f g dot equal to c2 f xx g plus f yy g. Okay. So now we have. So this means that we have the second derivative of g with respect to t. This one is that we have a second partial derivative of capital F with respect to x only, and this one is the second order partial derivative of capital F with respect to y only. Okay, so they are partial derivatives, and this is the second derivative because you have only one independent variable for capital G. Okay, so now you apply the so this is by 12.9.1. Okay, so by this equation you have that one. Okay, so now you so you have so you divide this product. You divide this product on both sides. So you will find that the g of that square c square g equal to f x plus f y divided by f is equal to k, a constant. Okay, which is a constant. Okay, so that is a constant. All right, and so we obtain one ODE. Okay, so it's g dot minus k c squared g equal to 0. For OT will equal to 0. Okay, so this is 0.9.5. Right, so for G, we have an ODE, and which is second order with constant coefficients. But the K is parameter. You don't know yet how to put the K. All right, and one PDE. All right, so the PDE is that we have fxx plus fyy minus k times x equal to 0. Okay. For all xy in the rectangle. So this is 12.9.6. Okay. Okay, so now our two-dimensional wave equation will reduce to one second order ODE and one second order PDE. Okay, now so we will solve the second order PDE first. Okay. And basically, this is the as we know, this PDE, second order PDE, is the linear elliptic PDE. Right? This is the elliptic type. Okay, and already in the normal form already. Okay. So of course you can solve the problem with what we suggest by using a complex characteristic coordinate. Okay, but because of this involvement of F into here, so it is better to solve this PDE by using again the method of separating variable. Okay? So next we let the capital F to be H of X and the Q of Y. Alright? So now we just again we apply the method of separating variable once again. This time, right? Here. So that we have we find that we actually have the Q H double prime plus H Q double prime minus K H Q equal to 0. Okay. All right. So you put this product into here, you get this equation. And so when you divide this by H times Q, so you have so actually you have 1 over H H of equals to minus 1 over Q, and here is Q minus KQ. Okay, and it equals P, again a constant. Okay, so P is constant. Alright, so we obtain two ODEs. Okay. Right. So we have H prime minus pH equal to 0. Okay. And we have Q prime minus K minus K minus P Q equal to 0. Okay, so we have two such this one depends only on X, right? So you know this one depends only on Y. So that's why we said they must be equal to a constant. This constant does not depend either X no N1. Okay, so that's why I have. So now, so h is a function of x, q is a function of y, so that's why we have this one. Okay, and this is the 12, 7, 12, 9, 8, 5, 6, 8. Okay. Okay, now the boundary condition. Okay, in 12, 9 boundary conditions. 2, yeah. Okay. Says that u x y p, okay, this is 0, right? And so it's h of x u of y, g of t. So this is 0. I have to say this is 0 for all x, y in the boundary, and for all t with 0. Okay? Right? Since gt not identical to 0, not identical to 0, so that at least one of t, that gt is not 0. Okay? We must have that h of x, q of y is 0 for all points in the boundary of the rectangle. Okay. Now that this implies that because that for all boundary points, the product must be 0. So that means that h0 equal to 0, ha equal to 0, and q0 equal to 0, qb equal to 0. So this is the boundary condition. Okay, so we have the boundary condition. Okay. There is the only way you can go. That because the boundary is here. It's either in this boundary, the x-axis is 0. In this boundary, the x-axis, but the y is 0 and the y is b. X is 0, x is a. Okay. So, right. Okay, and so so we have two boundary conditions for the second order ODE and second order ODE there. Okay. So basically, actually, we have solved such ODE with such boundary condition before, so that so if P is set is equal to if P greater than 0, right? So then a general solution of 9.7 general solutions is h of x equal to a e mu x plus b e minus mu x. Okay, and find 12.9.9 by the two conditions. We have A equal to B equal to 0. So there's no problem. Okay, so this implies that h of x is identical to 0, and which is not interesting, right? We are not interested with such trivial solutions. Now, if p equals 0, okay, then again a general solution of 12.9.7, it's h of x equal to ax plus b. Okay, and again by the boundary condition here, a equal to b equal to 0. So basically, if p is positive or 0, we have no solutions. So similarly, if k minus p, if we want to solve this equation, is positive or 0, right? The solution of 12.9.8 and 12.9.10. So this ODE together with these boundary conditions, all right? Is trivial. Okay, so we are not interested. We are not interested with such trivial solutions. Okay, so the final thing is that so now consider p equal to minus mu square, which is negative for mu greater than 0. Okay. So a general solution. Okay, so a general solution of 12.9.7. This one. It's h of x equal to a cosine mu x plus b sine mu x. Okay. By this boundary condition, so by 12.9.9, okay, we have a equal to 0. We have h0 is a, which is equal to 0, and h of a is equal to b sine mu a. With b not equal to 0, so we have sine mu a equal to 0. This implies that mu can only take m pi divided by a, and the m belongs to the set of all positive integers. So just as before, so we have that before. Okay, so for hm x, so with p equal to minus m pi divided by a square, we have a solution which is hmx, which is m pi x divided by a. Okay. Now, so next, consider k minus p, which is equal to minus mu square. I use nu. So nu square, which is and the nu will be 0. So a general solution 9.8. Here is gy equal to c cosine mu y plus b sine mu y. Okay. So again, by 12.9.10, we have G0 equal to C equal to 0, and the GB equal to D sine mu B equal to 0. So with B not equal to 0, so we have sine mu B equal to 0, implies that mu should be equal to n pi divided by B. Okay, so actually we just repeat what we did before, right? And so this is new here. Okay, so with k minus p equal to minus n pi divided by b square, the qn y is sine n pi y by b. Okay. So we put together now p is equal to minus n pi a square. K minus p is equal to minus n pi b square. Implies that the k is equal to minus pi square m square divided by a square plus n square divided by b square. Alright, so we have k now here. So the ODE in our original 12.9.3, okay, becomes to G double dot plus C square pi square, okay, C square pi square, and M square divided by A square plus N square divided by B square, and G. So that is the situation. Okay. So the ODE is a general solution. Okay. So the general solution is that GMN P is equal to Mn cosine lambda Mn P plus E star Mn. Why we put Mn? Because the parameter now is Mn here. Okay, and the sine lambda Mn P for t greater than equal to 0. Where lambda Mn is equal to the square root of this quantity. So it's c times pi, and the square root of m square divided by a square plus n square divided by b square for all m and in the set of all positive integers. Okay, so this is the so basically we solve okay. So I think I round up with my time. All right, and so we can use the two initial conditions to determine E and N and the E and N star. Okay, so we can use the two new conditions. But when considering general solution of U x y t equal to summation h n to g. Maybe I wrong it. Because for every m and for every n, we found out a solution, right? And the solution is obtained by using the method of separating variable. So actually, this is equal to h m q m y and g m and t. Okay, by superposition. Okay, all right. So this is equal to summation m from 1 to infinity, summation m from 1 to infinity, and e m n cosine lambda m n t plus e m n r sine lambda m n t times sine m pi x divided by a times sine m pi x divided by m pi y divided by b. Okay. For all x in between 0 and a, for all y between 0 and b, and for all t greater than 0. By superposition. Okay, so we can use the two initial conditions, right, to determine the unknown coefficients when considering a general solution of our wave equations. Okay, with the boundary conditions 1, 2, 1, 3. Satisfying the boundary conditions. Okay, under is 2. Under condition is 2. Yeah, 2. So and the method is very straightforward. So I think I have to stop here. All right, and our midterm exam number 2 will cover up to this section. Okay. So I will list all the sections that will be covered in midterm number 2 later on. Okay. Yeah. So please. This section, please read section 29 of the textbook, or and my piano. Yes. So the rest is quite standard. Okay? So similar to what we did in the previous sections in chapter 12. Okay, but you have to finish the rest of this section, right, by yourself. Okay. Any questions? Alright, so if no, then that's it. And I'll see you next time.